Solana protocol does not guarantee data availability. Avocado's state compression has no data availability guarantees for compressed account data. When account data runs out of rent, it is replaced with a hash that is persisted by validators while the data itself is deleted. In order to restore or decompress this data, a transaction uploads the original data which validators check against the persisted hash. Why is this significant, and what does it mean for Stellar moving forward? The significance of Avocado's lack of data availability guarantees lies in the potential risks it poses to the security and reliability of the platform. Here's a breakdown of the key points. Data loss. If account data is deleted before it can be restored, it is permanently lost. This can lead to significant financial losses for users and erode trust in the platform. Security risks. The reliance on validators to check the uploaded data against the persisted hash introduces a single point of failure. If validators are compromised, the system's integrity could be compromised. Performance issues. The process of restoring deleted data can be time-consuming and resource-intensive, potentially leading to network congestion and increased transaction fees. Implications for Stellar. The comparison of Avocado to state archival on Stellar highlights the potential advantages of Stellar's approach. Stellar's state archival. By providing data availability guarantees, Stellar ensures that account data is always accessible, even if it runs out of rent. This enhances the platform's reliability and security. Competitive advantage. If Avocado faces issues due to data loss or performance problems, Stellar could position itself as a more secure and efficient platform for users and developers. Trust and adoption. A strong reputation for data reliability can be a significant factor in attracting users and gaining market share. In essence, Avocado's data availability shortcomings create an opportunity for Stellar to differentiate itself and potentially gain a competitive edge. By emphasizing the security and reliability of its state archival feature, Stellar can build trust and attract users who prioritize data integrity. Solana protocol does not guarantee data availability. Avocado's state compression has no data availability guarantees for compressed account data. When account data runs out of rent, it is replaced with a hash that is persisted by validators while the data itself is deleted. In order to restore or decompress this data, a transaction uploads the original data which validators check against the persisted hash. The problem is, the Solana protocol only persists and maintains the availability of the hash, not the data itself. The hash can't be reversed to get the original data, so while the protocol can verify that the data is correct, it can't actually store or generate the data. Rather, it's the responsibility of the user submitting the transaction to come up with the original data. The question is, how can a user actually find this data? The proposal does not discuss data availability. Unlike with the index compression piece of Avocado, account data is not stored in Merkle trees, and there doesn't appear to be any mechanism to maintain the data at the protocol level. I assume this responsibility will be left to RPC nodes, a common design on Solana. The issue is, Solana RPC nodes are already very expensive to operate today, as in 512 gigabytes of RAM expensive, and this will put more on their plate. It's easy to imagine that a cost like this will ultimately be passed down to the user, making decompression expensive. But even more worrying than the price is that there is no guarantee or requirement that RPC nodes faithfully store this information. Once deleted, the account data payload isn't required for consensus, so approaches like proof of replication won't work. There's no way for the Solana network to guarantee that RPC nodes actually save the deleted data. RPC providers can choose to ignore compressed data because it's too expensive to store, or might pick and choose and only store compressed data that's valuable enough to be profitable. Think about it. If the protocol isn't forcing the RPC to store all data, and if storing the data is getting more and more expensive, the RPC provider may look to cut costs to turn a profit. If an RPC provider is faced with the choice to store your NFT that you thought would moon or a whale's USDC balance, one can begin to guess which data will be prioritized. If you care about getting your data back after it's archived, build on Stellar. While off-chain RPC nodes on Stellar Cache archived state, all data is backed by protocol-level guarantees. Validators routinely publish archival snapshots that contain not just the hash of your data, but the data itself. Every Tier 1 validator maintains these snapshots and offers them publicly for free via the Stellar Network History Archives. And who's storing these archives? Not only some of the most trusted names in the blockchain space, but also traditional finance as well, including the Fortune 500 company Franklin Templeton. The key distinction between Stellar and Solana lies in their approaches to handling archived account state. This difference carries significant implications for data integrity, accessibility, and network performance. Stellar's method ensures that all account data, even if archived, is replicated and readily available. By storing archived account state in a Merkle tree and publishing it to publicly accessible history archives, Stellar guarantees data integrity and accessibility. This is in contrast to Solana, where archived data is less accessible and its integrity relies on RPC nodes. Stellar's approach to archiving is inherently decentralized. The history archives are public and verifiable, eliminating the need to trust a centralized entity for data preservation. This is a crucial aspect for a blockchain network aiming for decentralization. The public availability of history archives allows for independent auditing and verification of the network's history. This transparency enhances trust and accountability. The availability of historical data can open up new possibilities for applications and research. For example, it can be used for analyzing trends, building historical analytics tools, or developing new financial products. Stellar's commitment to data integrity, availability, and decentralization through its archiving mechanism positions it favorably for future growth and adoption. By providing a robust and transparent system for handling archived data, Stellar can build stronger trust with users and developers. While not explicitly mentioned in the quote, Stellar's approach to archiving can contribute to scalability by efficiently managing historical data. The ability to provide auditable and verifiable historical data can be crucial for meeting regulatory requirements in various jurisdictions. The availability of historical data can foster a vibrant ecosystem of developers and applications built on Stellar. In summary, Stellar's method of handling archived account state is a strategic advantage that strengthens its position as a reliable and transparent blockchain platform. TPS decreases, network congestion increases. Solana has historically had periods of high transaction drop rates, such as in April 2024, when bot trading activity caused too much congestion, and Solana's networking layer couldn't keep up with the transaction volume. While Solana was able to improve the situation in a patch, blockchains are fundamentally network-bound when it comes to performance, and network congestion will continue to be an issue as the number of users, validators, and transactions per second increases. With Avocado, congestion will only get worse. Today, users and bots have to burn fees to submit transactions. These fees help prevent network congestion, because without these fees, attackers and bot traders could overwhelm the network with spam. Fees act as a deterrent and make such attacks too financially expensive to be practical. Yet even when charging fees for transactions, Solana has had significant congestion issues, and Avocado will throw gasoline on the fire. With this proposal, validators will be paid to send more transactions. Let me say that again. Solana, a network that already has a problem with transactions causing significant congestion, is proposing to actually pay validators for sending a new category of transactions, incentivizing even more transactions on the already overwhelmed network. When an account runs out of rent, it's not automatically deleted like account state. Instead, a compression transaction uses zero knowledge proofs to delete the account and add it to a Merkle binary trie. This trie contains all the compressed accounts, but validators only need to store the root of the trie, kind of. In order to use a compressed account, a user must submit a transaction with a proof of the entry generated from the complete trie. While technically validators only need to store the root of the trie to participate in consensus, RPC nodes need to store the full trie to produce proofs. Additionally, validators can make extra money by storing the complete trie and submitting compression transactions, and the network depends on these validators for compression to work properly. This seems like a poor design trade-off. Solana already has a problem with too many transactions when transactions cost money, and with this change, validators will be compensated for sending additional non-user transactions. You might think that this isn't so bad. After all, it's just one transaction compressing multiple accounts. There will be few more transactions than you would otherwise, but you can save so much storage space. The issue is, Solana is designing arbitrage spam directly into their network at the protocol level. Since validators make money sending these transactions, it probably won't take long for validators to compress all the pre-existing expired accounts when this feature is first enabled. Once all the old accounts have been compressed, validators will be continually searching for new expired accounts. Whenever a new account expires, all the validators will race to be the first to compress it to get the reward. This means that whenever an account runs out of rent, every single validator will submit a transaction to try to be the first to win the compression award, resulting in a large amount of redundant transactions that all attempt to compress the same account. These redundant transactions will take up limited network bandwidth that could have otherwise gone towards user transactions, reducing overall transactions per second. With the state archival solution on Stellar, all validators deterministically archive the same entries on a given schedule, so there's no need to send additional transactions. This is very important as networking is the main bottleneck in blockchain performance. Anatoly considered deterministic compressions but decided against it. If all the validators have to do this deterministically, then all of them have to maintain what is currently in the binary tree, and that means that the entire state has to be part of the snapshot. While that might be true for Solana's Merkle binary tree, the Stellar network structures archived state much more efficiently. Instead of using one large tree to store all archived information, the Stellar network stores archived state in a collection of small, immutable Merkle trees. This means that validators can archive new entries by only storing a small tree of recently archived entries, while the majority of archived state is offloaded in history archives. Solana's Avocado versus Stellar's state archival, a comparative analysis. The core issue here is that Solana's Avocado proposal, designed to manage account expiration and storage, could potentially exacerbate the network's congestion problems. This stands in stark contrast to Stellar's state archival solution, which aims to address similar challenges without compromising network performance. Key differences emerge in several areas. First, the incentive structure. Solana incentivizes validators to compress expired accounts, leading to a potential race condition and increased network load. Meanwhile, Stellar has no incentive-based mechanism for archival, preventing unnecessary competition. Next, the data structure. Solana uses a Merkle binary tree for compressed accounts, which requires full tree storage for RPC nodes and potentially inefficient data management. In contrast, Stellar employs smaller, immutable Merkle trees, allowing for more efficient storage and retrieval of archived data. Then there's the archival process. Solana's compression transactions are sent to the network, adding to congestion. Stellar's archival, however, is a deterministic process without additional network traffic. These differences highlight the potential advantages of Stellar's approach: improved scalability. By avoiding the congestion risks associated with Solana's model, Stellar can maintain higher transaction throughput, enhanced network efficiency. The deterministic archival process and efficient data structure contribute to overall network performance. Stronger network security. Reduced network congestion can enhance the security of the network by making it more resistant to attacks. In essence, Stellar's state archival solution positions it as a more scalable and efficient platform compared to Solana, particularly in handling account expiration and data management. This advantage could be a significant factor in attracting users and developers seeking a reliable and performant blockchain network. Looking ahead, Stellar could further strengthen its position by leveraging its advantage. Clearly communicating the benefits of its state archival solution to the broader cryptocurrency community would be key. Additionally, continuously refining the state archival process to maximize efficiency and scalability is crucial. Finally, exploring new applications that can benefit from Stellar's efficient handling of large datasets will be important. By building upon its existing strengths, Stellar can solidify its reputation as a leading blockchain platform for scalable and reliable decentralized applications. Stellar validators only need to store a small Merkle tree with recently archived state. See Part 1 of this series for more. Crucially, this allows Stellar validators to archive entries on a deterministic schedule such that state archival requires no additional transactions, meaning more bandwidth for user transactions and higher transactions per second. Now, Avocado increases network costs. The entire point of state archival is to reduce the amount of state blockchain nodes need to store. This doesn't just include validators. RPC nodes should also benefit from state archival. Unfortunately, Anatoly has decided to use a single try to store all compressed account state. This is very expensive. To recap, here's who needs to store the entire compressed account state RPC nodes to produce decompression proofs and validators that make extra money from compression transactions. The only entity that doesn't have to store complete state are validators that don't send compression transactions. Storing compressed state is too expensive for the long-term sustainability of the network, so Solana's solution is to make RPC nodes and many validators store compressed state. As you can see, there's really no cost savings from Solana's state compression. Network fees will still increase in order to compensate the rewards for validators that need to store the full try to produce compression proofs. Off-chain fees will also continue to increase, as RPC nodes are just as expensive to run as before, if not more expensive. While some validators won't need to store the archive try, the network still depends on validators that do store it. This doesn't seem to be a significant benefit, especially at the cost of higher fees, more complexity, and more network congestion. The issue is, by using a single try, archival state cannot be sharded. Any node that interacts with compression or decompression needs to store all compressed state, whether that be an RPC node producing proofs or a validator submitting compression transactions. The Stellar network has a much more scalable design. Because state archival on Stellar uses a collection of small, immutable Merkle trees instead of one large, mutable try, archival state is much cheaper to store long-term. RPC nodes don't need to store all archived state to produce proofs, but can shard trees between multiple nodes or elect to only store shards that contain certain relevant archival state. While history archives must maintain the full archival state for data availability and decentralization purposes, operators can also shard trees across multiple nodes and store archival state on cheap network-backed storage devices. Solana's single try cannot be shared, and since it is mutable, must be stored on expensive local NVM drives. The result is that with the state archival design for Stellar, the network actually gets cheaper. No validator or RPC instance needs to store all archived state, so builders will see performance and cost-saving benefits. Why is this significant, and what does it mean for Stellar moving forward? Key points to note. Stellar's state archival is more efficient. It uses smaller, immutable Merkle trees, allowing for easier storage and management. On the other hand, Solana's state archival is less efficient. It uses a single, large, mutable try, which is expensive to store and manage. Stellar's approach reduces costs. By allowing for sharding and distributed storage, Stellar can significantly lower operational costs for validators and RPC nodes. Conversely, Solana's approach increases costs. The need to store the entire compressed state increases costs for validators and RPC nodes, ultimately leading to higher fees for users. Stellar's approach improves scalability. The efficient storage of archival state contributes to higher transaction throughput and better network performance. Implications for Stellar are substantial. Lower operational costs mean reduced storage requirements for validators and RPC nodes, leading to lower operational expenses. This could make Stellar more attractive for new participants to join the network. Improved network performance by freeing up resources allows Stellar to achieve higher transaction speeds and lower latency, enhancing the overall user experience. Enhanced scalability, through the ability to shard archival state across multiple nodes, enables Stellar to handle increased network load and growth more efficiently. Competitive advantage. Stellar's state archival solution positions it as a more scalable and cost-effective platform compared to competitors like Solana, potentially attracting more developers and users. Potential for innovation. The efficient management of archival state could open up new possibilities for building decentralized applications and exploring novel use cases. In essence, Stellar's state archival design is a cornerstone for building a more scalable, efficient, and sustainable blockchain network. It addresses the challenges of state bloat and high operational costs, making Stellar a strong contender in the blockchain space. Thanks for watching. To let me know if you watched and listened to the entire outline, please type XLM FTW in the comments. We will see you on the next one.